So if we do the calculation, right, we use a power series. We say y equals to infinite power series. Then we can find y prime, then y double prime. Then we plug back in to this equation. We can get this. We can get a relation between m plus 2 a term and the m term has such a relation, has this scalar. So the current term and the skipping one term, the next term, so the relation is this, is with these scalar relationships. It'll be good for you to do this, okay? You y equals to power series, and then you find y prime, then y double prime, then you plug in, right? Then you will get this relationship. Okay, do this for yourself. And so this is m plus 2, right? If we keep going evaluating for the even terms, we will get this relation with the C naught. This is scalar. Okay, so the even term with the initial term is in this scalar relationship, and the odd term with the first odd one has this scalar relation. So then we can write this way. We can write C to M equals -1m A to M times C naught. We can write this way. And then this one, we can write like C1. So the atom, you can write in this way. We basically call this scalar A to M. We call this scalar A to M plus 1 term. So mainly just in this form, all right, in this kind of form. So the general solution to Legendre's equation is as such. C naught A to M is the scalar, this scalar. X raised by 2m, right? Alternate series, -1 raised by m. This term, and plus C1 of this one, A to M plus 1, this scalar. For the atoms. Okay. So let's see if alpha equals n. We have some special cases, right? If alpha equals n, remember what's alpha? Alpha in the beginning of here, alpha plus 1. If alpha is a positive integer, right, then what happens? A to M will be 0. Alpha is a positive integer. So this is A to M. Positive even integer. Even has to be even, right? Because A to M is all about the even terms. Then we have this. So in that case, this is a polynomial of degree n. But this one will be a non-terminating infinite series. So just for some special cases, if alpha is a positive even integer. If this is a positive odd integer, then the odd terms will disappear, right? Because that's always the odd terms, alpha minus 1, alpha minus 3, so on and so forth. So similarly, and these odd terms will be a polynomial degree n. And then the other one, the even ones, will be a non-terminating infinite series. So if n is an integer, then nth degree polynomial solution of this Legendre equation with n, so we just change alpha, use n, is denoted by this, p with full node n, and it's called a Legendre polynomial of degree n. So we'll see more about how to solve Legendre's equations and in notes 15. Okay. So this is a regular equation. We have ax, we have function of x to be a coefficient of y double prime, another function of x to be coefficient of y prime, and a function of x to be coefficient of y, then equals to 0. And we want a, b, c, those three functions, have no common factors. If then the point where if this one is 0, if the coefficient of y double prime is 0, a singular point of this equation, right? So let's see an example. We have this equals 0, Legendre's equation, and this clearly has a singular points at x equals to plus minus 1. Remember that? Let's review a little bit. Because in this case, this is our a of x, this is our b of x, this is our c of x, right? Then we want to change to be in the form of y double prime plus p of x y prime plus q of x y equals to 0. So p equals to this b of x divided by this a of x, right? Then this is the q part. And the 1 minus x squared, so in that case, once we change to be y double prime plus p of x y prime plus q of x y, we see that this 1 minus x squared is in the denominator, right? So which means x equals plus minus 1 will not be in the domain of p of x. So that causes singular points for the equation at positive 1 and negative 1. That's the concept from previously. So we will focus our attention on x equals 0 is the singular point. If x equals a were a singular point, we could always make a substitution, right? So t equals to x minus a. We use this momentary variable for x minus a. So then we would always have t equals 0, right? Because x equals to a. We make t equals to x minus a, so t will be always 0. Just a little trick. So we want to consider the equation of this form, right? This homogeneous equation, where A, B, C are analytic at x equals 0, which means analytic means has power, can be represented, the functions can be represented with a power series at the point. Right? That's what analytic means. Excuse me. So in general, if A of x equals 0 at x equals 0, we will not be able to solve the equation with a power series. However, in certain cases, we will be able to generalize the power series approach. Okay, if at any moment, if anyone has any question, feel free to stop me. Let's say this Bessel's equation. Bessel's equation has a singularity at x equals 0. So this is x squared y double prime, xy prime, x squared y equals 0. We divide it by x squared. So get this form. Now this 1 over x is our p of x, capital letter p of x. And this y coefficient is 1, so q of x just 1. Right. So p of x is b divided by a. Q of x is c divided by a. So we get a 1 over x and 1. So we'll see that we'll be able to generalize the power series approach if p of x approaches infinity no more rapidly than 1 over x, and the q of x approaches infinity no more rapidly than 1 over x squared as x goes to 0 from the right. If we rewrite this one in the form of this, so use this little p of x. So little p of x over x. So this capital letter P of x, is 1 over x. So the little p of x is defined as x multiplied by capital letter P of x, which we see from Anchi's presentation. So this little q, lowercase q of x is x squared multiplied by capital letter of x. So we define the following. The singular point of 0 is a regular singular point, so we add a regular in front of a singular point. So we know it's a singular point already. Now we add this regular in front of singular point. If the function lowercase p of x and q of x are both analytic at x equals 0, which means x times capital letter P of x and x squared times q of x are both representable in power series. Otherwise, we just call it irregular singular point. So we have two kinds of singular point. Right? Singular point is for before we know it cannot be represented with power series. But now we multiply by x squared. So we multiply capital letter P of x by x. We multiply q of x by x squared. So we have two kinds. By doing such, so we get two kinds of singular point. One is called a regular. If, after doing this little trick, it becomes representable in power series. Otherwise, we call it irregular singular point. Just definition. Anyone has any question? Let's see this example. X squared y double prime. By the way, the Bessel's, so that one is the Bessel's equation. But usually when we see this kind of form, x squared as a of x equals x squared, and b of x equals x, goes Frobenius equation. So we divide by x squared, then we get this. So little p of x is x times capital letter p of x. So we get 1. Q of x is x squared times capital letter q of x. In this case, it's just 1. So we get x squared. So you can see both p of lowercase p of x, lowercase q of x are analytic at x equals 0, right? Because 0 is in the domain of this function, and 0 is in the domain of this function, right? Because if p of 0 is 1, q of 0 is just 0. So x equals 0 is a regular singular point for this equation. Similar to Anchi's presentation. Now consider this equation. Of 3x to the 4th power, a of x, b of x is x squared, and the c of x is this negative 2x cubed plus x squared. Now we want to transform to p of x, q of x. So we divide every term by a of x, which is 3x to the 4th power. So now we get a p of x, capital letter p of x. Capital P of x is this. Capital Q is this, negative of this term, capital Q. If we want to rewrite, we can rewrite this way, right? Because 1 over 3x squared can be written as 1 over 3x, then divided by x again. Same thing for this 2x plus 1 divided by 3, then divided by x squared, right? Because this can be simplified. X cubed, x squared, 3x to the 4th power. We can factor out x squared. That becomes 2x plus 1 divided by 3x squared. So we can be written in this one, can be written in this, because we want to multiply by x squared. So if we multiply this one with x, right, we got 1 over 3x. You don't really have to do this, all right? You don't really have to do this one. Just you go from here. We multiply by x with this, so we get 1 over lower p, lowercase p is 1 over 3x. Lower q is multiply x squared with capital Q, so we get 2x plus 1 divided by 3. Now, 0 is not in the domain of p, little p, right? So which means 0 is not, which means a p of x is not analytic at 0. So little p, lowercase p is not representable with a power series. And since the limit of this, so the right limit goes to infinity. The left limit goes to negative infinity. In any case, you just see, okay, 0 is not in the domain of this one. That's more obvious, right? So 0 is not a regular singular point in this case.
Quick
Yes.
question.
Yeah.
So if it's not a regular singular point, it doesn't mean that it's not. No, it means that it's an irregular singular point, right?
Right. Yes.
Okay, got it.
So we separate it into two kinds, regular and irregular. Let's see this example. Determine if 0 is an ordinary point or a regular singular point or an irregular singular point, right? So last class we talked about we have an ordinary point and a singular point. Now we separate a singular point into regular one and irregular one. So we have three kinds now for this equation. So a of x is this, x squared times 3 minus x. B of x, 5x plus x cubed. C of x, 2x minus 3. X equals 0 is a singular point because we see x squared, because if we divide everyone by a of x, so a of x will be, so p of x will be this one, b of x divided by a of x. So x squared times 3 minus x will be the denominator in the p of x. Same thing for q of x. So we see 0 won't be in the domain of capital letter P of x, right? Because we have x squared times 3 minus x in the denominator. Yes, right. So this is our P of x, capital P, capital Q. Then we multiply by x, right? We multiply, so this can be simplified, right? X is a common factor of the numerator and denominator. So this is simplified to be this. Now we multiply x with this capital P. So we get 5 plus x squared over 3 minus x. So 0 is in the domain of this lowercase p. Similarly, we multiply x squared to capital Q. Then we get q of x to be this. Again, 0 is in the domain of this lowercase q. So that means both little p and little q are analytic at 0, right? So 0 is a regular singular point. Anyone has any question? All right. The method of probabilities. So this is a typical x squared, typical Frobenius differential equation. So what do? We're gonna go back to our trick. We say, okay, let's guess the solution to be x raised by r. Remember we did such thing before, earlier in the course. So this solution, so y equals to x raised by r, and the y prime equals to r times x raised by r minus 1, y double prime power root, y double prime, r times r minus 1, x raised by r minus 2. Now we substitute back into our differential equations. So we get this. We simplify this, multiply x squared times this, right? X times this. So we get, so simplify, we get this. Now we can factor out x raised by r. Simplify this. This we see can be factored. So because what's our goal? Our goal is to solve for r, right? This is similar to as before. And solve for r. So r equals to -2.5. Okay, so we have two solutions. We have x raised by half, square root of x raised by -2, 1 over x squared are solutions. So notice, even all of the coefficients of our original equations are analytic at 0, but the solutions are not, right? Because this will have 1 over x squared. right? 1 over x squared. So in general, but from the beginning it's okay. But in this case, so in general we have to solve for x. So we want to do this trick, right? We multiply x with this p of x. So this is our p of x. So we want to call this little p of x. So we have this x times this p of x. Before we call this b of x, right? This is our a of x. This whole thing is our b of x. This is our c of x. So in this case, p, little p, and little q are power series. So then we want to get a solution to have the power series form of this x raised by r times this power series. Right. So in this case, we see the exponent of x becomes from n becomes n plus r. So our power series is started with x raised by r. Okay, because we want to deal with situations like this. The infinite series of this form is called a Frobenius series. So it may not need to be a power series, as r may not be a positive integer. For example, r equals to negative half. Right? R could be a negative number. Then we will have x raised by a negative half, then x raised by half, so on and so forth. So we have some rational, we could have some rational expressions, rational terms in the solution. So let's see this example. So let's solve this equation. Right? So P of x is a power series, and Q of x is another power series. So we represent it as such. So now let's assume a solution is this. So x raised by r times our original power series. So that changes the power of x to be x raised by n plus r. So the initial C naught not to be 0. So we want the series must have some non-zero first term. So we differentiate this. So y prime, that's n plus r times Cn, then now x raised by n plus r minus 1, power root, right? Y double prime, n plus r times n plus r minus 1. Then Cn x raised by n plus r minus 2. I'll substitute this 3 into the original equation. So we get x squared times y double prime then x times xp of x times y prime, then q of x times y. Remember we have our p like this, q like this. So x squared times, I read it out, y double prime, something like this. X times P of X Y prime, which is read out like, plus dot, 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 read out a couple of terms. Q of X times Y. Anyone has any question? So this just, we read out the first couple of terms for this one. This was just read out a couple of first terms for this one. This just 2 terms for Y. Then we want to simplify this, right? Because we have x squared times x raised by r minus 2. That becomes x raised by r. And we just simplify it. Simplify. Now we want to collect the coefficients of x raised by r. Similar trick as before, right? So we factor out x raised by r, and the rest is simplified to be like something like this. And then we see this has C naught, C naught, C naught. We can factor out C naught as well. Then we just have this coefficient. Because when the power series is 0, that means all the coefficients 0, especially for x raised by r term. But it's not x raised by r to be 0, so just forget about that term. So it means we have this. And we want C naught not to be 0. Remember from the very beginning, we see, okay, I don't want C naught to be 0. So if C naught not 0, then this is 0. So that's r times r minus 1 plus this p naught r plus q naught equals 0. It'll be good for you to go through these calculations, all right? Go through these calculations. So this last equation in the Frobenius method is called initial equation, all right? Just a name. And the roots are the exponents of the differential equation, right? If 2 roots are not the same, then there are 2 possible Frobenius series solutions. If they do equal to each other, then that's only one solution. And the second one cannot be found with this method, so we can find 1. So notice P naught and Q naught in the initial equation. P naught, Q naught, are just the values of P of 0 and Q of 0, right? Anyone has any questions? So this is new to us. R times R minus 1 plus P naught R plus Q naught equals to 0. Okay, let's see an example. We want to find the exponents and the possible Frobenius series solution for this equation. So A of x is x squared times 1 minus x squared. B of x is 2x. C of x is minus 2. So we want to change to be in the P of X, Q of X form. So we divide every term by A of X. Then we get coefficient of Y double prime to be 1. P of X, capital P, capital Q. Because X squared, we have 2X here. So add 2X cancel out with 1X, X raised by first power in the. So we have 2 over X times 1 minus X squared. Then little p of X will multiply X with this capital P of X. So X times 1 over X disappeared. This X in the denominator cancel out to be 1. So lowercase p is 2 over 1 minus X squared. So P of 0, well, this is 0, so I have 2 divided by 1, which is 2. Q of X is multiply capital Q with X squared. Then we see this X squared term cancel to be 1. So little q is minus 2 over 1 minus X squared. And Q naught is Q of 0, which is negative 2 over minus 0, which is 2 over 1, which is minus 2. Then we plug in to R times R minus 1 plus P naught R plus Q naught. So we get R times R minus 1 plus 2R minus 2, or which this equals 0. We solve for R, right? We have this quadratic equation, can be factored. Then we get 2 solutions, negative 2 and 1. David, question?
This equation at the top of line 8, this came from basically the whole process that we went through in the last problem. Is it like skipping steps? Like
No, this is called a Frobenius method. So Frobenius method end up with this initial equation.
Okay, is it always that?
Yes,
Okay,
for Frobenius method, for using this method.
I see. Thank you.
You're welcome. So R is solved. R equals negative 2 and 1. So the 2 possible Frobenius solution is this. The first solution is X raised by R, while R is negative 2, and this power series. Right. So that becomes X. So we can simplify this one. So it becomes X raised by n minus 2. R equals 1. So this is X raised by 1 times our power series. Anyone has any question? So we're learning a new method called Frobenius method, and using this initial equation. Okay, theorem. Suppose 0 is a regular singular point for this equation. Let's see the row greater than 0 positive number denote the minimum of the radii of convergence of a power series. Right? So this is our power series, this is our power series. We have some number, a positive number, to be the radius of convergence for this one, the radius of convergence for this one. So let R1, R2 be real roots, and the R1 might be the big one of the initial equation. So this is our initial equation. Then we can see something, A, B. You can see for X being positive, there exists a solution of this such equation of this form. X raised by R1 multiplied by our power series. And A naught, the first term, we don't want to be 0, corresponding to the large root R1. First one, first part. For X being positive. So there exists a solution for this equation of this form. B, if R1 minus R2 is neither 0 nor a positive integer, then there exists a second linearly independent solution for positive X of such form, X raised by R2, then multiplied by the power series. And similarly, B naught corresponding not to 0, corresponding to the smaller root of R2. The write-out of the convergence of power series for Y1 for the two solutions are at the least row, right? So this row is a positive number. The coefficients in this series can be determined by substituting the series in the differential equation. Okay, let's see some examples. We want to find the Frobenius series solution for such equation. A of x, B of x, C of x. We always want to change to be P of x, Q of x. The coefficient of y double prime is 1. So we divide by A of x. So get this. We get x divided by 2x squared. This is 1 over 2x. Or we can write it as this. Because when we multiply by x, this just goes away. We have a half. Similarly for this one, we divide by 2x squared. We can write in this case, once we multiply by x squared, we just get this numerator. So we see once we multiply by, so the lowercase p is just half. The lowercase q is this quadratic form. And the 0 is in the domain of the constant function. 0 is in the domain of quadratic function. So 0 is a regular singular point. So the initial equation becomes, well, this is our, so P of naught, P of 0 is a half, Q of 0 is negative half. So we have our initial equation. Then we simplify, we multiply by 2 on both sides. It's easier to see it. We multiply by 2, we get a 2r squared minus r minus 1. We can factor 2r plus 1, or 2r plus 1, then r minus 1 equals 0. Or you can deal with it. If this half is too difficult to deal with, you just multiply by 2 on both sides. Otherwise, it's just factored like this, right? R plus half, R minus 1. Because minus 1 plus half gives you a negative half. So we got two solutions. R equals a negative half and 1. Right? So this is the bigger one is R1 because we want R1 to be the big one. So 1 minus negative half, there's 1 plus half. Oh, hold on a second. In this case, R1 is the first one. Negative half. R2 is this one. So this thing is neither 0, of course it's not 0, nor a positive integer, because we're treating this one as R1. We're treating this one as R2. So we should get two Frobenius solutions. First, yes.
Didn't it say in like the theory that R1 is greater than R2 or equal to R2? Like on page 8 in the theorem?
That's right. That's right. That's right. Yeah, sometimes the type O. So,
Like if you go, yeah.
oh, no, that's for, yeah. Yeah, so this thing, let R1, R2 be real roots, and with R1 be the great one, be the big one. Forget about this, okay?
Okay.
Forget about this.
So how do you decide which is which?
It's kind of difficult, right? It's kind of difficult because you can call either one, R1, R2.
And then you just treat it differently depending like on the A and B, I guess.
Yeah, but maybe I have to change the notes. Let's change the notes to be this one. Let's see. R1 is a big one. Maybe it should be R1 be the smaller one. It's difficult to tell. It's difficult. R1. Let me think about this one. Yeah, I found this. I found this mistake when I was talking. It's not consistent. Because it's difficult to tell which one is R1, which one is R2. Okay, this is a dilemma. How do I do this? You know what? It's the opposite. To make this work, I need to choose R1 to be the smaller one, not the big one. Okay, that would work. So switch this sign. So let R1 be the smaller one. All right. Let R1 be the smaller one, not the big one.
For this case.
No, just in these notes. Just choose this one. Yes, for this theorem.
Okay.
For this theorem, right? Let R1 be the smaller one. So switch this inequality. Then choose the R1 to be smaller one. So the smaller one minus the big one is neither 0 nor a positive integer, right? So we will get two Frobenius solutions. So x raised by R1, and then this one is x raised by R2. In this case, just negative half and 1. Anyone has any questions? Yes.
What is the purpose of we suppose to figure out R1 less than like R2?
Just a theorem to use.
Oh, okay.
Yeah, just a, just to, theorem is someone already
Set up.
already
Oh.
Yeah, already set up exactly, and we're just trying to use it.
Oh, you just like before we have R and R1, R2, either one we have like two solution, and then we just pick R1 and R2, either one. That's it. So I don't know. So now
Yeah,
we
but
had the purpose.
but to be able to use this theorem, let's pick R1 to be the smaller one.
Okay.
So
Right.
change this inequality to be less than or equal to, because
Right.
we want to make any theorem useful. All right. So now we want to substitute negative half and 1 into the equation, into a differential equation, and solve for the coefficients in terms of those roots. So we substitute R1 with negative half, R2 to be 1. So we have n plus R is y with n plus R. On y prime, we have this n plus r. This one, y double prime, have this, right? Okay, so so this is a lot of calculations. Right? We have to go back a little bit. So I have to go back a little bit. So 2x squared x minus this. So we have 2x squared times y double prime. We have x times y prime. We have this times y. Then we try to simplify. You see this x squared and this is minus 2. So x raised by n plus r minus 2 plus 2. That becomes x raised by n plus r. This is x times this x raised by n plus r minus 1. That also changes to be x raised by n plus r. Right. And this one will have x squared, x raised by n plus r. That becomes x raised by n plus r plus 2. Right. This is 1, so we still have x n plus r. So notice this, right? We want to change, we want to reindex. We want to reindex because we don't like this x raised by n plus r plus 2. We want to change this one to be somehow to be x raised by n plus r. So we can factor out x n plus r with all those terms. So we reindex this. Right? We reindex this. So n equals 0. N equals 0. We have r plus 2. Now we will reindex. We want to start n equals to 2. N equals to 2. So which means you could think k equals to n plus 2. Okay. So k equals to n plus 2. So this n plus 2, you substitute into k. So you have a k plus r. Okay. Then this k equals n plus 2. So n equals k minus 2. So you have this one change to be k minus 2. Then you just change back k into n. So your n start with 2. Now this one change to be n minus 2. And that one just change to be n plus r. Now we have our x exponents, same exponents, right? We have x raised by n plus r everywhere. So we can factor out x. So this has x raised by n plus r, this has x raised by n plus r, this one same, this one same. Now we can factor out the coefficients. We can factor out the coefficients. So, but because this term skipped n equals 0, n equals 1, so we can handle it separately. Okay. For this one, when n equals to 0, we get 2 times r plus, times r minus 1. 2 times r minus 1. For this term, n equals 0, we just have r. Okay. For this one, n equals to 0, well, just 1, just minus 1, right? So when n equals 0, so I have this. Simplify it, so get this. So we have r squared minus a half, r minus half equals 0, right? Get it from here. N equals to 1, we substitute n equals 1, so get this. We simplify it, we get this. So we solve for this factor r. So this one is not 0 for r equals negative half of 1, right? Because from so r equals negative half or 1 from the beginning part of it. Okay, so now, so those two are special cases, right? So when n equals 0, when n equals 1, now we can talk about n starting from 2. When n starts from 2, we just, have this one plus this one minus this one minus this one, right? Like this. So, we simplify again, keep simplifying. So get a relationship between Cn and the Cn minus, right? So get this relationship. So Cn and the Cn minus 2, they are with this scalar relationship, 2 over this. So case 1, when R1 equals to negative half, because we have two solutions, negative half and 1. Let's substitute in. So n plus negative half, n minus negative half. Do the calculation. So in the end, you get this, right? Because this an just this Cn. Right? So get nth term and n minus 2's term have this scalar relation, 2 over n times 2n minus 3. So the odd term, we can do some calculation. We see the odd term equals 0 for all n. So what about for even term? For even terms, if n equals to 2, we can substitute in this way. So A2 substitute in 2A0, A0, then 2 times this, we see A2 equals to A0. Substitute n equals 4, we get this relation. A4 equals to A0 divided by 2 times 5. Similar as before, keep evaluating when n equals 6. We want to see the pattern. N equals A, we see this pattern. So in the end, we see that's A0, n's factorial. See 2 times 3 times 4 times 5. Because this is 2n, 2 times 4, right? Because A is 2 times 4. So you can see, and 6 is A 2 times 3. 4 is 2 times 2. So we see n factorial. Then we have 5 times 9 times 13. Well, they differ by 4, right? 9 minus 5 is 4. 13 minus 9 is 4. So that's 4n. We see that's 4. Then 5 start with, so because n, think about this, n is 4, right? We have this 9. So 4, so 5, 4, 4n, so n times n times 4, so 4 times 4, 16 minus 3, that's for this one, that's for 13, right? That's for this 13. If n equals to 3, we have 9, n equals to 3, 3 times 4, 12, 12 minus 3 give us 9. If n equals to 2, if n equals to 2, 2 times 4, that's 8, 8 minus 3, that's 5. Get this 5. Okay, so we get to the even terms with the relationship with the first term, with this 1 over n factorial, then over 5 times 9 times 4n minus 3. So this scalar. Anyone has any question? Now let's see. So okay, so the solution is, just put back in. So this is the nth term, right? We can write out a couple of terms, or we write in a summation sign. The r terms 0, so have this a naught times x raised by r1 negative half. Then with this one, the even term survives. So that's for r equals to negative half. So have this solution for the equation. Now let's see r equals to 1. R equals to 1, we put it back in, r equals to 1 from this Cn, right? R equals to 1 now, r equals to 1 now. So we simplify, in the end to get this relation. The nth term and the n minus 2th term with this scalar 2 over n times 2n plus 3. And again, this starts with 2 when n equals to 2. So same thing, C1, if we do evaluate at 1, starting from 1, we get 0. So that implies all odd ones are 0. For the even ones, we get second term is 1/7 of the first term. Then 4 equals to 2 times 2, so 2n, n equals to 2. We have this, n equals to 3. We have this. So we observe we have 2 times 3. We can evaluate n equals to 8. Right? Then we see the pattern is n factorial. The denominator we have 7 times 11 times 15. That all differ by 4. And we set 7 with 3. What's the relation? Right, 3. This is 15. The last one is 15. This is a 3. So 3 times 4, that's 12. 12 plus 3, that's 15. In this case, that's n is 2. 2 times 4 is 8. 8 plus 3 give us 11. So the nth term is 4n plus 3. So get this relation. So the 2nth term with the first term is with this scalar 1 over this. So we have a solution, right? Write out a couple of terms like this. Write it out in summation sign like this. Any questions? This is quite tedious, huh? Let's go back and review a little bit. So we're trying to solve this differential equation. Right. From ax, bx, cx, we want to write it into p of x, q of x. Then, because 0 is a singular point, right? And then we want to, and it's irregular because once we multiply x with p of x, we get a little p of x half. We multiply x squared with capital Q of x, we get this little q of x to be this. So now 0 is in the domain of those two functions. That means 0 is a regular singular point. Then the initial equation, because this is called a Frobenius method. This is our initial equation. P naught is P of 0, Q naught is Q of 0. So we use this initial equation and we factor out, we get two solutions for R, -half and a 1. Then we just think a solution to be like this. But before it's x raised by n, but now we multiply x raised by r with our infinite series. So solution, we guess a solution to be like this, x raised by n plus r. We differentiate again, so we plug back in. We plug back into our differential equation. Tedious calculation. And our goal is to make the power of x to be the same. So we can factor out the x term. So in this case, we want to factor out x raised by n plus r. This term, no problem, because we multiply x squared, that kills this -2. This term, no problem, x times x raised by -1, so that becomes x raised by n plus r. This term, we have problem because we have x squared. Once we multiply out, we get n plus r plus 2. So how do we get rid of this plus 2? We reindex. So we reindex, we want n start with from 2. So now we have x raised by n plus r. Well, this term is x raised by n plus r. So that means we can collect the coefficients of x raised by n plus r. But because we started with 2, so we need to handle n equals 0, n equals 1 separately. This is not a big deal, all right? Sometimes it can be ignored. Because, you know, when you deal with pure mathematics, finite terms, it's not something, a lot of times not taken into account. So the coefficients, we collected the coefficients of x raised by n plus r term. We simplify. In the end, we get a relation among the terms. So in this case, we get a relation of the nth term and the n minus 1's term, n minus 2's term. Well, n minus 2 is our first term, C naught, right? Because n starts with 2. And start with 2. If we take n equals 2, right? The starting point. So get nth term and n minus 2's term with this scalar 2 over such denominator. Now we have two solutions, -half and 1. So we just plug back in. -half for r. Tedious calculation. Because we're trying to find out the relationship among when r equals to -half among the terms. Right. So A1 will be 0 if we plug in 1. Plug in n equals 2. Plug in n equals 2 because n start with 2, right? We get A1. So A1. Oh, this we don't have to consider, right? Then 2n plus 1, the atoms, they will all be 0. Then for the even terms, we'll find the pattern similar as before. We find the pattern, then we form like 2nth term, the even terms. We see the 2nth term has a relation with the first term with this scalar 1 over this. So we can write out our solution. Right. When the second one, R2 equals 1, we do the same thing. We do the same thing. So C1 will be 0 implies every C1 in this case is B1, right? B1. The atom B1 will be 0, implies all the atoms will be 0. Then we just have to evaluate sum of the even terms. So 2, 4, 6, or maybe you want to do 8. Then you find the 2nth term. 2nth term, like this. Then the solution from r equals 1 is this. Lots of calculations. So the general solution would be the R1, from R1, the solution from -½ and the solution from 1. Anyone has any questions? The calculation is tedious. Okay, let's see another example. So back to Bessel's equation. All right, we want to use Frobenius method. Of course, dividing by x squared, we get this. So this is our capital P, capital Q with just 1. Then multiply x with this P. So the lower P is just 1. Lower Q, just x squared. P of 0 is 1. Q of 0 is 0. So our initial equation becomes this. It's just r squared equals 0, right? Because minus r plus r is 0, so it's just r squared 0. Just so r equals 0. Then the solution in this form, just x raised by r, with x raised by 0, which is 1, with this series. Well, then that's our y, that's our y prime, that's our y double prime. Plug back in to the equation. Right. We have n minus 2, but this is x squared. We have n minus 1, but we have x here. So no problem once we multiply. But this one, we have x squared times x raised by n. We need to reindex this one. So we reindex. Think about n equals to, well, k, another index k equals to n plus 2, because we want to start with 2 now. So k equals to n plus 2. Then n equals to k minus 2. So this Cn becomes k minus 2, C k minus 2. And n plus 2 equals k. So we have x raised by k. Then we just change back k to be n. So n start with 2, Cn minus 2, x raised by n. Now x raised by n, x raised by n, x raised by n, we factor out that. X raised by n, x raised by n. So now what do we get? We get n squared Cn minus 2. Well, when n equals 0 for this one, what happens? We have x raised by 0, which is just 1. When n equals 2 and the second, okay. So now, if n is 0, that's 0. So we just left with this. The first term, n equals 1. And starting with the 2. So this is gone. This one just C1 times x, and this one. So two special cases, right? N equals 2, we just get those two coefficients. The n squared Cn minus 2. And just get this, or this equals to 0, we have this relation, Cn's term and the Cn minus 1 term. So n's term and n minus 2's term with this scalar relationship, negative 1 over n squared. So n equals to 2, 4, 6. Plug in to try to find the pattern. So the pattern is this. So negative, positive, negative, positive. So get an alternate. Negative 1 raised by n. So I have 2n squared. 2 squared, 4 squared, 6 squared, 2n squared. That's a 2 to the 2n. 1 squared, 2 squared, so on and so forth. And this can be written as a 2 to the 2n's power n factorial squared, right? Because we have 1 squared, 2 squared, 3 squared, so on and so forth, n squared. So that's n factorial squared. So our solution has this form. Anyone has any questions? If C naught is 1, so we get the Bessel function of order 0 of the first kind. So we're only able to find one solution for this one, for this equation. So later we will find a second linearly independent solution, okay, which is not a Frobenius, not by Frobenius method. For Frobenius method, we can only find the first solution. Okay, just a lot of calculations, but the idea is the initial equation. Okay, the difference, the new thing is the initial equation, basically from Frobenius method. Frobenius method, just this initial equation. And anything else is very similar from before. Anyone has any questions? So this is new to us. I know some of you missed some classes. You may have problems to do the corresponding homework, but every class is recorded. Okay, so you need just to watch the corresponding recording. And we had a lot of presentations, almost every homework, you know, is being presented. So you shouldn't have any problem if you watch the recordings. Anyone has any question? All right, I'm going to stop.